Andhra to Bangalore, and Bangalore to Chennai. Yeah. So Chennai is where the flight is the night time, early morning.
You are not staying in your. Is there anyone here?
Yeah, I do have. I think I'm staying actually before going to that. So my sisters are there. Yeah, my parents just passed away 2 years back. So I have a house still. So I'm just going to go there and just check it out, and then I'll leave. So just because in India, you know how it is. Nobody lives there. I still have stuff back then, everything. So I just have to go there, make sure that everything is, otherwise they break.
Yeah.
That is always my answer. People know that nobody lives there. So I just have to go and just pay attention and then because there are so many things held up. We do a lot of proposals. That's a big thing for us. Yeah, we write a lot of proposals because the success rate is about 70%. So most of our time is spent on and advising students. We have a deadline CDC, right to be conference and decision. CDC end of the month. Yeah. The ACC final papers are due in next week. I just said to my students, they have to do the CDC, ACC, they have to submit. So,
The CDC preliminary first is
no, it used to be, but now I heard it's end of the month.
okay.
Yeah, they changed. Because ACC conflicts, the final version and this. So usually March 1st used to be my deadline when I was a student. Then they moved it to 15 because they used to have problems with the ACC. Because the final versions are due exactly same time as that. So now what they did was the ACC deadline got pushed, the final version. So now they are pushing the CDC deadline. I think 27 or 28 is the deadline. The CDC deadline.
It's just hard.
Yeah. The ACC final versions are due and so, but there are always something, when
If we want to training,
Yeah.
if we want to do this one, the whole thing,
yeah, I think that and he already started creating some problems, using source code books. So, I think he's doing it. Yeah. So, I think it's.
So, sir, this year, sir, this is our curriculum will be.
Oh, I see. Then there's also, I can give you some suggestions. There is you might want to consider environmental control. Okay, that is a very good course. I offered.
So far, I have thought that all together this is without only
Right.
EBS system, non-EBS system,
Right.
class and second semester.
Right.
You want we have to now this
Adaptive control. You have adaptive control. Those are four courses. Right. And you could have network control systems as one. But no network.
I have thought
You need to have that. That's fine. You can either change the name, but either you can bring in, but you can cover fuzzy and all, you won't have time. So just make it as a network control, and either you name it as running base. I think that would be a very good because then you have
all our suddenly India is pushing, not India. Is pushing, but also they are telling that one machine learning course is compulsory for ethics. They are pushing for 3-4 courses. Why electrical
So we offer one course called Computational Intelligence, which is machine learning. It has the fuzzy neural network, evolutionary computation, all that fun stuff.
Nowadays, these people don't even know. I think nowadays we have numerical computational.
Now they don't.
They don't understand exactly matrix equation is a problem. You cannot make them understand that it is a problem. How do you think? Because they don't have the kind of course. You only have course, you understand that. Because we know that how it has to be made in machine.
Makes sense. The only way you can have this, I was looking at some curriculum in other campuses. Remember, every year we had courses like thermodynamics. So many of them, right? Yes, strength of materials, civil, those are courses that. So I don't know now, but what I know is yes, statics, dynamics, yeah, so but that you have to have. I would say statics and dynamics you should have.
Otherwise, we are not getting into physical science of the problem.
The strength of materials you can eliminate. Okay, thermodynamics I think is necessary, but you can also eliminate because the problem is for W's you may need it, like for those working in power plants.
So we also have fluid dynamics.
Yeah, I know. I also took that, but I don't think we have that now. We can do it because you're bringing in programming, and then some course on like the data structures or something you're bringing in, right? So you cannot be able to accommodate.
Yes, so many.
But you cannot only courses. Don't talk about it. Yeah, don't talk about it. That's your goal. You can have a third semester machine learning, like often, mostly the techniques and stuff, right? Neural network, those kind of things. That's it. Then when you going ahead, you bring in control.
Yes, sir. People are not understanding. We are trying to think it as AI should be third semester. Third semester, yeah, but this people basic user algebra course they don't have.
Yeah, you should have that. Yeah, I know. I think yes. No. Yeah, we can bring it in last year, in the first or second. Yeah. You know what I mean? Because unless you bring some other stuff in there, right? It's fine. Okay, good morning everyone. I think it's 10:05, so we thought maybe we shouldn't be delaying this and overshoot the lunch time. But before I start, I know yesterday we had the first tutorial. So I want to get some feedback. I know Professor Vera spent a lot of time and I also were discussing this because how do we make sure that we have this done? Because this is the one where we're going to learn a lot more. I'm kind of flipping slides. You're looking at what the material is, but when you run the, when you take that MATLAB code and break it down, like he did nicely, he was explaining how you split it into different parts, right? I think then you run it, in the process you would learn more, okay? So my question now is, how many of you completed what Dr. Vera mentioned yesterday? Okay, so problem 1 full, all of it, and you got similar results, right? The inverted pendulum? Okay. Up to the 3, okay. 2, okay. So, but then in the problem 2, there are several subs. You also completed that. 2 cases. Okay, so that you can do today. Right, I know. Sure. I think that's the right way to do it. That's exactly what we wanted you to do. So go back to the slides and then cross-check
the math, you put the dimensions. Otherwise, you won't understand what GIAN. See, this is exactly what we want to do. I'm happy that. So at least you guys came in the problem 2 second part. So how about anybody else? Huh? So how far are you in the problem one? So you done till 4, case 4, okay? Okay. Yeah. I think you want to. So my suggestion is, I want you guys to finish once you do the first problem, it's actually very easy for you to do the second one. The only thing is you may have to deal with the dimensions. But otherwise, I think it's the same process. It's a different system. It's the same process, right? So I think that's the only thing, but try to get it done today. Today afternoon we don't have any lecture, right? So I would encourage you to finish this today. This way, if you have questions, you can ask, number 1. Number 2, you remember the second tutorial. I think it's tomorrow, right? So we may get into some stability and beyond that. So this is why I think it's absolutely essential to understand how we are modeling that NCS, how the controller is working, you learn, you know what I mean? I think those kind of things you want to have definitely a good understanding. And remember, as we are moving along, we will get into neural networks. It's a little more complicated compared to the Q-learning. Q-learning is pretty nice, and it's a linear system, A and B, right? But when you get into neural networks, it's a little more complicated, and you have to deal with the actor pretty, you know, sometimes those problems. I think so. It was, I know, I think so. So I think, I agree, thank you for pointing out. There should be a code for intro to oral. That's what she was bringing it out. There were 2 problems we had. One is the policy iteration. That's the basic for reinforcement learning. I also encourage you to run it and understand that. Although in many of my lectures, I usually cover that without the NCS. Then I go, even today, I'm going to cover that. Neural network, actability. Then I would go into the actual. So there were some slides that were duplicated. Primarily I did that so that it's more like a recap. Okay? So I know many of you didn't have that background. So therefore, good thing I did to kind of duplicate so that I'm covering the same material, you know, part of it. And this is without NCS. Then you basically get into the NCS. That's the only difference, right? So, but remember, it gets a little more involved. Because as we are putting more nonlinear system, linear system is much more easier. Okay? So I think try to finish the intro to oral code. Make sure at least you run it. And make sure it works and you understand what's going on. And keep the slides so that you cross-check. That's absolutely necessary. This is one way you learn how those math equations are, or the code in there corresponds to what is in the slide. Okay? And then I think when we deal with the next tutorial, it's a little more involved. Okay? So that's one thing. And as we also mentioned, the assessment, they will be very similar. There will be different system, and you guys will have to do this. And within what, 2 hours? 2 hours. So make sure you're familiar with those, you know. It shouldn't be that hard, honestly. And that shows that how well you guys do. I know it's compressed 2-week thing, you know, but I think if you do it, this will be a good course. Honestly, a very good course. It could be more than one. You know, you have the neural network part in the machine learning side, and you have the network control system. That's what we were discussing with these 2 professors today. How can we make this? They're making revision in here. I'm positive when I go around, there are stuff going around. And the source code that I provided, even though it's not the way that I would like to see, but still, I think what Professor did was, he's kind of splitting it, that essentially you could do that and have it as a curriculum in your campus. Yeah, right, that's right. So that essentially, and you know, I know everywhere these things are getting pushed. It's a big deal right now in terms of jobs. Okay? Any other questions, guys? Any other questions? Huh.
manageable system if we consider it as an NCA system.
Right.
So how to choose the delay and the control system? Because in the board there is some language.
Right. Okay, so that would be a design issue. So what happens is, so her question is that if you are dealing with NCS system, so I provided or we provided all those values like a delay, this and so forth. So how do you determine that? So one thing you need to do is like when you are about to design an NCS system, first thing you need to know is what type of network you're going to have. Is it a wired network or is it going to be a wireless network? A lot of us prefer wireless. Okay? But wireless, there are challenges because wireless bandwidth is a lot less than a wired system, right? So you have to deal with that. Second, how many of those systems you're going to share on the same network? So let's say you have a batch reactor stuff running in a lab environment. Think about you have a wireless network. Under the same wireless network, you have multiple subsystems, right? A batch reactor, inverter controllers, etc. So then you need to realize that that bandwidth will be shared. So when you share the same bandwidth, you're going to experience more delay. See? So ideally what you'd like to do is, you probably look at, okay, my bandwidth will be split by simple thing is average. So you take, if you have 4 systems, you divide that total bandwidth by 4, and then from there you compute the delay that you may have. Usually the network would give you an idea what is the maximum delay bound, usually, the type of network. And then you can look at it if it's wireless, usually the protocol will be IEEE 802 or something like that, .15. If it is a wired network, Ethernet, you have a TCP/IP. So based on that, they give you what is the delay bounds. And once you know that, then you can determine what is the delay D bar. So that D bar is very important. And the packet losses usually it's modeled as a Bernoulli distribution. That's what we did here also. You see? The Bernoulli distribution. And so once you, that's the only spec that you need. Also, when the packet drops are always Bernoulli. The only thing is the delay, basically. What is the so nowadays I think it's a wired network, with this Ethernet, you have a pretty good bandwidth. Nowadays I don't know here, but in the US we are looking at like 1 gigabit, so it's quite fast. So I don't know here what is the is it a Cat 8? I don't know what these cables are. IT people would be able to tell you because the Cat 8 cable can go up to several gigabits. So that means that you are talking about delays are very, very small. You see? And so, but it's not just the delay, it's the combination, the delay and the drops is what makes it a challenge. Okay? Any other questions, guys? Okay. So, yeah, you can define. One is the cost. Remember that you define the cost. Actually, cost is the most important because when you define the cost, you are putting both the error as well as the input, right? So it's kind of combined. So you can actually define like other indices, right? The steady state error. You can also define the overshoot. You can add all those actually. You can do the settling time, the ones that you deal with in the undergraduate. Yeah, other transitions, yeah. And remember, in addition to it, there are other ones, like in the ITA criteria. Remember those? Yeah. But those need, exactly, those need these information like error and everything. So, I don't think we have anything you can use. Go back to your undergraduate, yeah. But the cost is absolutely necessary. The cost will tell us whether which one is better. Yeah, because it combines both the state or the error, tracking error, and the input. Whereas some of the other ones don't consider the input. So you could have a higher input, but lower, better performance. But the input is also one of the criteria. We really don't have a whole lot of input, right? So I think that's very important. Yeah. Okay. Any other questions, guys? Any other questions? How about you? Were you able to get it? I know you had a version problem.
I saw the first problem case.
You finished? Okay. So it worked. Okay.
So in the third case is it was some syntax error.
Right. Right.
And then in second problem I tried.
So what did you do in the first one when you had the syntax error? How did you?
First two there was no syntax error.
There's no first two parts. But how about the part three? I know you had.
For idea they are showing the syntax error.
Right.
So I tried to find substitute. So there was ICAN and Lucati something kind of syntax.
Right, I know. I think that there doesn't work because the versions they updated some things. Yeah.
So I tried to solve with OD 45 and I can't
Right.
syntax.
No. You can't use
Some
OD.
issues.
Right.
So still
You know what you should be able to do is maybe you can. I don't know. How do we?
No, actually, time being, you can share with.
Right, that's what I was thinking. Yeah.
And later on, he will update.
You can update your MATLAB. That's the other option. Yeah.
Here it cannot be done.
Yeah.
The MATLAB, your licensed version we are using, but it needs credential.
Right. I know you are not a student. You probably have access issue. Yeah, I know.
That is there.
Yeah. So you are using what version?
207.
117. Wow, that's quite old. Yeah. So this is a discussion we had actually, because the issue was always the versions. We can't plan which versions. So the most recent ones we can do. So yeah, maybe what you can do is you can work with one of them, and I think they're all staying in the same Australia. Maybe you have to find some time talk to them. And maybe you can just see how you can at least run it. Yeah. I know you know MATLAB. It's just that you want to get that feeling that whether you're able to run and you can kind of cross-check those slides. Because I don't know, the other thing is how assessment-wise, what
We see because one she having some problem with laptop, so I told her okay, you can use my
right. But you can't provide laptops for a lot of people. Like he's also same issue. I think.
We see that.
How we can be done. I think we have a few. Otherwise, the people who are coming from outside is the main thing. At least luckily their laptops work, and he's the only one. Maybe this is what we need to think.
No, okay. For him, I can provide actually in my lab one PC is there.
Okay.
Where advanced version is not there.
Yeah.
So on the time of exam, I can shift there to.
I think that's all. Because the others shouldn't be having a problem.
No.
Everybody has right. You guys have the credentials, so you shouldn't be having that problem. Yeah. All right. Any last question before I move on? Any last minute question? Yeah.
How can we optimize the repetition gain?
I don't think you can. There is no result that optimizes. But let me say this: the discrete time work we have done, it connects at least with learning rates. Whereas the continuous time, there is no connection at all. So, like if you take a course on continuous time adaptive control, for instance, all those adaptation gain, you just say that it doesn't give you the bound. In discrete time, at least you have the bounds. So if you look at it, the learning rate, we have a bound. 0, alpha should be greater than 0 and less than something. But in actual continuous time, we don't have it. So, but you can't optimize it. So you have to really. In other words, what it shows is for a range of values, it would work. The question is, how do you pick a value out of that range? Is the question. I don't think we have a way to do it. In other words, there is no relationship, at least we could get, to either optimize it or whatever. I think it's a very difficult issue. At least I'm not aware of. Okay? All right. Okay, so I think we kind of still going ahead. So today will be lecture, we're looking at lecture 6. Okay, so you saw that we had two quantizers, we have a linear system, and we kind of went through some material about what is a traditional quantizer. And we also talked about the dynamic quantizer. Remember that? So what I wanted to kind of do today is we may want to look at the nonlinear system. This is linear. So in the nonlinear, I kind of covered quickly the neural network-based optimal control. Because that's what I keep saying, that I keep going around and trying to cover that material. And if you remember this, you have x of k plus 1 is f of x of k plus this, and here is the value function. This is the cost to go, and there is a terminal constraint like we said, and n is the final time. So it's the same thing. So you write the Bellman equation. So the Bellman equation is the optimal value function at k to infinity or k to n is equal to cost to go, or from k to k plus 1, and then from k plus 1 to n. So it's kind of a recursive equation that you are trying to do. Okay? So in that code that I provided, you need the partial dynamics. If you remember that, you don't need f, but you do need g. So that's why I think she said that intro to oral MATLAB code, I think you should want to run that code. And it's shared by Professor Vera, right? It's shared. So I want you to run that. Okay? And then you have the one-time step ahead information is also needed here. You can see that is x of k plus 1. But how do you relax the g? So that's what's the fundamental issue. The only way you can relax g for a nonlinear system is explicitly you go with an identifier. So what does the identifier do? You remember, you write this equation f and g as a neural network because this is nonlinear. So you write it as a neural network. It's a single layer because you only have one layer of x. And sigma f should form a basis. So you are expressing this, and then you're combining sigma f and sigma g. And so these weights are kind of combined. So you only need one neural network. So then you define an identification error between you assume the state is measurable. So you define the identification error x minus x hat, and that error is basically will be used to adjust the weights. So, but before you do that, you construct a augmented system with history. Look at that. X of k is xk, x of k minus 1 up to k minus n. So you're constructing the data and you're saving that data for the last few sampling instants, and you are building a vector x, capital X and capital theta, and then you are constructing the set of weights and you are doing this. Now the purpose of doing this, now why are we constructing these delayed values? Can somebody tell me why? So why are we constructing? You remember that? We are constructing, that's my question. Why do we need that? Okay, what are you saying? That's correct. But why? That's my question. Why do you need it? I think the answer is in equation 2. Why do we need it? No, there's no optimality there, right? There's no optimality there, but
2 is the update law. So,
yeah, 2 is update law, just to update the weights.
So weight is related to what?
So you see the update law. Update law uses the history. Remember that, right? That you guys understand. Why? Simple. You see the inverse, there is a term with inverse. That term is not invertible if you only take one instant at one instant. And there is a condition. What is the condition adaptive control? We did talk about it. I know some of you have taken adaptive control. What is the condition? Okay, you guys need to look at the slides. There is a condition called persistency of excitation. I did explain that. So the persistency of excitation condition doesn't satisfy if you're only taking one value at a time. So you have to construct kind of a matrix, and unless that condition is satisfied, that inverse that of the whole matrix doesn't exist. So that's the reason, the PE condition. So that's why I said equation 2. The equation 2 is, you remember this is a matrix. It has to be invertible. This can't be done unless you construct that history. Okay? That history makes that matrix invertible. That's basically what we call persistency of excitation. Okay? So, and you see that all this is also a vector based on the history. So this is also a different dimension than x of t, just like the NCs. Okay? So all this, a lot of people call this as data-driven control, because you're using the data from the system and you're also saving the data also in the real time. All this is a real-time control, right? So you have a buffer in the same processor and you are storing that information. Don't forget that. Okay? So the update law, you're generating the update law using least squares. And once you do that, then you get the update law and we prove that the identification error converters. Okay? So by doing this, once you have done it, then you can unpack this. You can unpack the W, and that W has both F hat and G hat, both F and G. Okay? So then, now you're getting into the controller, like I explained yesterday. So the controller has to have two neural networks, one for the value function, V hat. So V hat uses another network weights, and you see that n minus k. So the basis function is varying with respect to time. And for a finite horizon, it has to vary. So it's n minus k. N is the final time, k is the current value. Got it? So that sigma v uses not only the state vector, but also the time. Okay? So that is v hat, and then there is a terminal constraint. Remember I said for finite horizon you also have a terminal constraint. Okay? So, and then you construct the Bellman error. So the Bellman error is coming out of this equation that we talked about. So this is the Bellman equation, V star. So we use the same equation and construct the Bellman error. And so you see that Bellman error equal to you move that V hat from the left hand side to the right hand side, and we call that as a temporal difference error in reinforcement learning. Okay? So temporal difference. So temporal difference is because this is k plus 1, that is k, and there's a difference in time. That's why it's called temporal difference. It's just time-based error. Okay? So this EKB is the Bellman error, and you have the neural network stuff along with the cost to go. And then you also have the constraint error, terminal constraint error. Then what you do, you sum that up to get the total error, and then you have an
update law for the weights, for the critique. So look at this weight update law. This alpha v is the learning rate. The learning rate for the critique. Okay? So what does the critique do? Critique approximates the value function. Don't forget that. So the word critique means it's trying to critique the performance, whether it's good or bad. In psychology, these things came from psychology. So like in a human brain, it critiques how well is the actor is going to do. So that's what it's doing here, okay? So basically you have alpha v. Alpha v is mainly the learning rate, and you see that sigma 1 and all that, and you use that total error to adjust the weights of this particular critique network. Understood that? So, yeah. Okay. Is it better? Still down? Okay. So that is the critique weights, this is how we are doing it. Now, somebody can raise this issue. How did we come up with the weight updates? Now, remember I said, what was the answer? How did we come up with these weight updates, either the identifier or this one? What is the process of arriving at these weight equation, update equation? How did we get that? Although I'm not showing you that, the derivation, what did we say? GIAN stability. So the book has the proofs. I think you may want to go back and look at it, okay? So all these update laws are basically being derived from the GIAN stability. You see? So if you don't use these update laws, there's no guarantee that your closed loop system is stable. In this case, uniformly ultimately bound. And why is it UUB? Because you have approximation errors for the neural net. Okay? So you are doing that and you are showing that update law. Okay? Now you do the actor. So the actor is another neural network, and you see that there is one W hat of Q, n minus k, and then you come up with a error, action error or control input error. Control input error is generated by using two ways, U1 hat and U2 hat. U1 hat is basically the output of the network, actor network. U2 hat is generated by half or inverse. Look at that G hat. So I'm replacing the G with the G hat from the identifier. And then you're taking partial V hat over partial X of K plus 1. Even if I take partial V hat, I still need the G. You see? I still need the G. So you can make an assumption and say, I don't need a second neural network, I'm going to assume G is given. That's what I did in the intro to our code. Here we are assuming G is also unknown, and we are using an identifier. So totally how many neural networks here? 3 neural networks. You can implement it. As I said, we have implemented this on a mobile formation controller, a mobile robot. It's published in our transactions on control technology. So you could actually show in real time, you could do that in 8086 processor. The only issue we had was memory, because we had 3 weights, the actor weights, the critique weights, and the identifier. So the storage was a problem, not the computations. And we have to swap. Remember, you need the old values. Remember, y hat of k plus 1 is w hat of k. So the previous value of the weights, you have to store them. And so that was the memory issue, the size of the network. And we had 3 networks. So computationally we are able to do it. It's basically the memory problems, because you have to swap when you are computing it. Okay? So, but you can implement it and then you can get that. But remember, what I'm using to tune this is basically used as the control input error or action error, U tilde. So whereas the actor uses the Bellman error, the critique uses the Bellman error, the actor uses the control input error. Now the question is, why can't we use the Bellman error for the actor? Why can't we do that? Now how many of you took the adaptive control? I know several of you. There you remember A and B. B uses U update. A uses E. They are the tracking error. Go back and look at it. Yeah. So if you look at the update laws in the traditional adaptive control, for A x dot equal to x plus du, updating A uses the track error, regulation or tracking error. The update for B uses the E cross product between E and U. Try it out. You can't use E because then it won't work. So the same way here we are using U tilde, whereas in the critique we use the Bellman error. Okay? So that is needed, and this is the only way we found. I don't think anybody, we came up with this, pretty much everybody using this. I don't think we have any better way so far. Okay? And you see that alpha U, this alpha U is the learning rate for this actor network. And so I don't have a way to select that. That's what the question earlier. But you can select using some trial and error. So here is the flow chart, pretty much. So you have an identifier. You can see you start with initial value and initial admissible control, U0. Then you have the identifier with the update class that we just showed you. Then you have the value function, V hat, and its update class. Then you have the action network, U hat, and its update class. And then what you are doing is you are checking whether you reach the final time. And if it's final time, you stop. If it's not final time, then you increment the time k equal to k plus 1 and you go back. Okay? So this is, so it has 3 neural networks, don't forget that. So this is nothing to do with NCS, but NCS is just uses the same thing, where we have the quantizer. I'm going to show you the quantizer. But before I do that also, we also has incorporated actuator saturation. So remember, we talked about saturation in the quantizers. We can also have saturation for the actuators. So a lot of times control methods do not consider the actuator limits. So what happens is the control signals are very large sometimes. If you don't choose properly your gains. But the actuator has limits. So sometimes it saturates, you have the same problem. So I'm going to show you as part of this how we can use the actuator saturation as part of the optimization. Okay? Any questions here? This is without just a simple actor critique neural network based control of the acting system, like a robotic system and stuff. So here I think the example, here are the, you see that, how the bounds are. I told you the bounds for the learning rates. You see alpha V has to be between 0 and something, and alpha, this has to be between, this is the identifier, 0 and theta I am, and you see that it also has some bounds. So what I mean is, those are given, the bounds are given, but it doesn't give you a specific value, how you select. You have to fit within the bounds. Okay, any questions here, guys? So there is an example, tooling robot. That's a very classical example. Okay, this robot, tooling robot is a feed system, and you have those values there, and you can, I showed you last time, nicely converges. So you see that there is identification error. When the identification error converges, then the system response converges and the control input also converges, and also you see that the weights in fact oscillate initially and nicely they are converging. And you can see also the Bellman error converges, showing that it is optimal, as well as the terminal constraint error. Okay? So unless the Bellman error goes to 0, we can't claim it's optimal. And that's why we want that. And the terminal constraint error also has to be going to 0, because see, this is a finite horizon case. Okay? So that's why we plot everything, and you guys can do the same thing from the code. Okay? And here we show that the weights are bounded and converged. Okay? So now, what I'm going to do is, I'm going to extend this to output feedback, then we go into the case of quantization. Okay? Because we want to show you the state feedback and output feedback, and so that's what I was trying to tell you. Okay? So, output feedback is very common because in industry, not every state is measured in practical system. So typically the outputs are measured. Okay. So now I'm going to stop a second here. I asked you to tell me, educate me. Remember that? Just like I'm giving you lecture, I asked you to check a few things, right? As anybody has an answer for any of those questions I asked you? Huh? You need to speak aloud. I want you to, you know what, I asked you a bunch of things. What's the difference between learning and adaptation? Okay, what else I asked you? Yeah, that's right. What happens when something is not controllable or something is not observable? And what else did I ask you? There are a few things. not one or two. Yeah, somebody wrote something. Yeah, let's look at it, what it is. It's very important. Huh? Yeah, what is FI? Yeah, we know FI. This is FI in the tooling robot. I asked you, what is the other class of systems that, I know non-affin is one example that she told, but non-affin is very generic. But there are other class of systems. Okay, and what else? What other questions? Yeah, why norm is always positive? Because we look at the norms. Everywhere we use the norms in the proof. So why do we need to study norms? Okay, what else? What else? Huh? Right. What is the difference between thank you. What is the difference between eigenvalue and singular values? Where we call singular values and where we call eigenvalues. Yeah, those are important. And what else? Okay, difference between stabilizing and optimal? Is it what we said? Okay, and what else? What is the other one?
Why do we need to check Lipschitz continuity?
Yeah, why do we check continuity, Lipschitz continuity? That's very good. That's a very fundamental question. Okay, what else? Yeah, I think, so anybody looked at any of these answers? Okay, which one? Right, right. That's what I am asking, yeah.
So, you can change with the control input. Or you can add some actuator there.
Okay, that's what I want. So, if system is not controllable, there's nothing we can do. The only way we have to do is physically change the actuator location or add an actuator. Okay? So remember, you're going to see this in industry all the time. Because the people who design, that's why I was telling you the mechanical people or somebody, aerospace, they design, but there will be a separate group doing the control. So when you model the system, you check it and you realize it may not be controllable. So that guy doesn't understand controllability and stuff. It's our job. So then immediately we need to realize that we have to look at the actuator and check that location. Either you move the location or you may have to add an extra actuator. Typically we change the location. Okay, how about the observability? You can add the sensor. But you know what I would suggest? Change the location of the sensors. That's what is observability is. Because that means that, remember I said, that example I gave you, the physician in the 16th, 17th century was watching the stomach digest food. What in the kaleidoscope example, what you do, you watch that what is going on inside the kaleidoscope. So the same thing, that physical system is like a black box. The states are inside the system. You're only seeing the outputs as it projecting out, and you're watching through the outputs what's going on inside the, all the states, what's cooking inside. So if your outputs are not in the right location, that means they're blocking the view of the states. Practically, that's what it means. The only way you can do that is by changing the location of the sensors or a type of sensor. Sometimes a particular sensor may not give you that, so that's what you need to do. And this is another one. So I know most of you know how to check controllability, but you need to understand practically what does it mean. Any questions? Okay, so we got one answer. So we need a few more. Anybody looked at any more, like singular values, eigenvalues? You check the norm? So you check the eigenvalues also? No. So what is the norm? Yeah.
Norm is representing distance.
Right.
Size or length.
Right.
Size or length and
Right. Right.
eventually it will be positive.
It's always positive. Yeah, that's right. So now, the benefit of a norm is, you remember in the weights and all, they're all matrices. So what norm does is it just squishes into a single variable. Okay? So it's kind of a like distance or some measure that kind of tells you if you have multiple variables in there, So is there a vector, you can try it out, or you could do it with a matrix. So that's what we do in the proof. We show that the whole thing is basically as one item, and we show that the whole thing is bounded, rather than looking at individual. It is always positive. It's a bound. Okay? So it's always positive. It's magnitude. Basically, it's providing the magnitude. Yeah. Okay, what else?
So adaptivity learning.
Yeah. So what is the difference? Yeah, that I don't think many of people know. So what is the difference in learning? Even that controllability, you ask anybody, that's not the problem. Learning and adaptation, what is the difference? So adaptation is what I showed you that update line, right? That is the adaptation. But what is the learning and adaptation? That's right. Learning is understanding how to do this. Doesn't matter what the adaptation comes in, right? But learning also includes, I'll tell you even more, learning also includes experience. Adaptation doesn't. So if you look at adaptive control, it uses the current value of the error. The learning, you saw that it uses the history and all other things. Remember? So like when I gave you that example, let's say you ride a bike. You remember I gave you the example, you're going from place A to place B, let's say from your hostel to the department, and there could be multiple routes. And so what you do is you're going on one route, let's say there's a construction going on. And so you have to use a different route, and you don't want to wait until something going on, construction like this. Otherwise you would wonder, how do you go? Let's assume that you're late to a class and you want to find a route. So that's basically, we talked about exploration, exploitation. So exploration, you're looking at, already you're finding different routes. And then you are trying to learn, which route would give you which is best. And if one of them is blocked, then immediately you realize, okay, I can go with a different one. So a learning essentially uses the history and our experience. Remember that. Adaptation uses that information and tries to adjust. So adaptation is an instantaneous process. Learning has a longer time interval. So there's a huge difference between learning and adaptation. This is just one of them, and we'll talk more. So this, a lot of times people don't understand, and so you wonder, why do we have to do the learning? So as a human, we learn, implicitly we learn, right? Because you are using your experience. Oh yeah, I have to do this. That's your learning, and in the back of your mind, we always have that. Adaptation is basically using that experience you are trying to adjust. So you might have realized the same problem. Let's say you go to a different place, you do the same thing. Okay? Alright, any other things that, what is the difference? You know the answer? Again, that's different, yeah.
So when linear transformation applied, then it only scales, but doesn't change its direction.
No, but that is but that's the process. But I'm asking you, what is the difference between eigenvalues? Eigenvalues are defined for a matrix, okay? And you're talking about eigenvectors, right? Now I'm not talking about eigenvectors, singular values. Well, if you diagonalize it, those are eigenvalues. Right, but what my question is, what's the difference between eigenvalues and singular values? Not eigenvectors and singular values. I understand. Eigenvalues give you the magnitude and vectors give you the direction. That was not the question. The question was between eigenvalues and singular values. And this is applied here to our work. That's why I asked you that. What's the difference? Okay, anybody has an answer? Okay.
I think singular values project
Is there any eigenvalue for non-square matrix?
I think you may want to look at it. Yeah, that's neat. He gave a hint. Take a look at it.
So we can represent a matrix in a model matrix.
Yeah. But anyway, I would say he already gave a hint.
So
Eigenvalues are only applicable for square matrix, but singular values can be applicable for anti-cross matrix.
For any matrix. So that's the major difference. But take a look at it. Yeah. I think you may want to look at it. We might have studied, but we never pay attention. You know? So I think it's, and the reason we do that here is because the weights are non-square matrices. Remember that. All the weights of the neural network are always non-square. So this is the one reason why we do that. Okay? All right, guys. So let's go back to the observer stuff. At least it's important. At least we got some answers. We were learning something here. Okay, so you have that x of k plus 1 is this. Now what I'm going to say is, let's assume that x is not measurable. In the previous design, we assumed that x is measurable, right? The state vector is measurable here. If you remember here I am assuming that state vector is measurable. Okay? So now I want to relax that. So I want to relax it. So what I'm doing is, here you see that outputs are only measurable, y of k. And so I have to assume that this system is controllable and observable. Otherwise I can't do that. And then I also need to assume the norm of this G matrix is basically bounded. Doesn't go up, okay? So now the first step is to design and observe. Okay? So the outputs are measured. So therefore I'm going to add and subtract a times x of k. Okay? So you could do that, a times of x of k. If I add and subtract, that subtracted value is combined with this nonlinear f. So f equal to the f of x minus a times x. So basically I'm not changing anything, right? Not changing anything. So once I get it, then a is selected such that it's Horowitz. This is not Horowitz, actually this is typo. No, this is not Horowitz. Discrete time, what is it called? In continuous time, we call that when the system is stable, all the eigenvalues are on the left hand, then we call that as a Horowitz matrix. In discrete time, what is it called? There's an equivalent name. It's called Schur, S-C-H-U-R. So check that out. The same thing, but in Schur matrix, that means the eigenvalues are within the unit disk. So that's a typo there. So A has to be Schur because this is a discrete time. Such that A comma C is observable, and that's important. So now you write it in this form, x of k plus 1 equal to a times x of k plus the neural network to approximate plus the approximation error. Okay? So now I'm going to design an observer. So my observer is estimating x hat of k plus 1 is equal to a is known times x hat. So that's the initial state. You start with the initial known state, x hat plus the neural network. Now look at that. Neural network is using estimated state. You see that? The neural network is using the estimated state. Now go back here. The previous case. Here I'm using the actual state as part of the neural network input. So that's the difference. You have to keep that very clearly. So in this case, x of k minus 1 or x of k you use directly because x is measured. In this case, in the output feedback case, x is not measured, so the only thing I am going to use is x hat. You see the difference?
Why here neural network you are using?
Why I use the neural network? Because f and g are unknown.
Okay, but here it is a and a b is not.
No, I think it's nonlinear.
Oh, not linear. Okay.
X of k plus 1 is f of x of k plus g of x.
Okay, it is written in the form of a of xk and a
You
form.
rewrite it, that's right. You rewrite it first before. And the reason is because you need to select a such that a minus lc is. So sure
condition has to be.
yeah, that's why you bring that a before you do the observer. So you do that, and then here you see that you are using that estimated state, and since f and g is unknown, then you have that f plus gu, and then L times yk minus c times x hat k. Yk is measured, c is known, xa hat is available, estimated value. So basically this is your observer, y hat is c times x hat. So you have to do this because A minus LC, L has to be selected such that A minus LC is on the left hand of the poles of the observer has to be on the left hand. So that's why we do that, okay? So now state estimation error x tilde is x minus x hat, and if you do that you get this equation, and where you see that the AC is A minus LC is a closed loop matrix. So you select L such that AC is shown, basically is inside the unit disk for the observer. And then you have come up with this update law, and then you can show that things are bounded, okay? So that's the observer part. Now remember, observer gives you the estimated state, x hat. So this observer was not there, this was something we have developed long time ago. And the main purpose was, you are estimating the state in the absence of the system dynamics. That question. Okay? Alright. So next, so now you design the same after printing. You have the U hat, look at that, U hat as X hat, everything is replaced X's with X hat, and action error, you see here X hat here X hat again, and then the same thing with the control. So everywhere, wherever there's X, you are replacing with X hat. So it's a lot more challenging when the state vector is not measurable. But still works. The design works, okay? So if you do that, here is the design. So initialize the system, you initialize the observer, you initialize the weights, then you update the observer, and then you update the identifier in order to get that weights, update the weights, and then you update the value function and critique. Only difference is you have the X, replace X with X hat, and also the control input. Now the proof changes. The proof changes because your inputs to the neural network is no longer the state measured X. It's basically X hat. So because of that, things change, the proof. So the proof gets more involved, and so it gets bloody, you know. So, but the flowchart is there, and we can show the same thing: boundedness of the observer, boundedness of the critique, convergence of the finite horizon, optimal control. So you can prove all that stuff works. Okay. So you take a Van der Pol oscillator, a different example. A Van der Pol oscillator, x1 dot equal to x2, x2 dot equal to this, y equal to x1. You discretize it, and you can plot that. And A matrix is given here. Okay. And you can see the A matrix, all the eigenvalues are within the unit disk. So you show the observer errors converge. You show the system response and control input converges, and you can show the Bellman error converges, the terminal constraint error converges, the weights also converge. Now the only difference is between the output feedback, it takes longer for the Bellman error to converge. Why? Why does it take longer? Why does it take longer to converge? Huh? States are not measurable, so the system is fighting. So first thing it does is it makes sure that X and X hat converges. So until that happens, then you can't learn the dynamics. Then it's the controller is trying to learn the dynamics, you see. So there are so many things which are unknown. So first the state, then the dynamics. Once you understand the dynamics, then you basically is able to do the optimization. So this is why it takes a little longer if you look at the plots compared to the case where when the state vector is measurable. So remember that the more it's uncertain, it takes more longer, right? The same thing for human too. So that's the main thing here, okay? So this is the control design, and okay, so now I'm going to stop here. We'll have that after coffee. It's correctly 11 o'clock, around 11. We'll take maybe a 5-minute break. So when you come back, then I'm going to show you the actual saturation as well as the quantization for nonlinear affine system. Remember, we looked at the nonlinear affine system. We also will look at, I think it's output feedback. Okay? Now that is. This is why I gave you the background without the NCS. Okay.
All right, I think we'll start. Otherwise, we'll be late for lunch. Okay? So what now we are going to do? We looked at, remember, state vector measurable actor critique, right? With 3 neural networks. And we saw one was identifier, and you need 2 more neural networks. Then we went to the case where the state vector is not measurable. This is a case, very typical, practical case, right? And then we did that part of that. So now we are ready. So now what I'm going to do is, I'm going to use the same affine system. I'm going to look at how do I design an optimal controller. The network is lossless, but we have quantization. And we're going to use the dynamic quantizing. You got it? We're going to use the dynamic quantizing. Okay? And then we also would deal with what we call actuator saturation. Now, actuator saturation is a big problem. Because a lot of times, you design a controller, the controller would give you a very high control input. Whereas you don't, in the actuator doesn't have that bandwidth to convert that command into either a voltage or a current signal, you see? So that's the problem. So actuator saturation is a very common problem, many practical situations. Now what is the alternative when your actuator saturates? You have to physically change the motor if it's a motor. And sometimes when you make the motor bigger, it becomes a load on the robot or the case. That's the reason why many times we are very careful about actuator saturation, okay? Then we also have quantization, okay? So online finite horizon, this is what we are trying to talk about it. So here is the system. Remember we saw this system, x of k plus 1 is equal to f of x of k plus g times x of k. And then here you see that this is a quantized input. Got it? And yk is equal to c times x of k. We assume that the system is controllable and observable, the same stuff, okay? And uk is through a quantizer, all right? So here is the performance index. The only difference is you see that this is non-quadratic, this WUI. This is non-quadratic. So that means that if it's quadratic so far, we made it as uk or times uk. That's quadratic so far we have been doing. But now, I'm going to define it like another function like this. W of uk equal to 2 times integral 0 to uk, phi inverse of v transpose r times dv. And what this is doing is, it's basically limiting the actuator output within a certain limit. Okay? So there is a saturation limit. It basically limits the control input between a lower bound and the upper bound. So this is non-quadratic, okay? This was taken from this paper, Levitsky, Optimal Control of Nonlinear Continuous Time Systems, Design of Bounded Controllers via Non-Quadratic Functionals, okay? So this is basically designed, this term. So this term is used here instead of quadratic, and then you have the Q, and then here is the terminal constraint. This is basically the value function. So this equation basically uses non-quadratic cos functional to accommodate the actuator saturation. And so non-quadratic, this is an example of a non-quadratic function we use as part of the value function. It's for finite horizon. Okay? And we also want to handle, along with actuator saturation, we also want to handle the issue of quantization. All right? So now, so this is the Lipschitz condition. You see that the Lipschitz condition keeps popping up everywhere. So now you form that equation into what we call the Bellman equation, which is a recursive equation, Q plus W plus V star. So you see that the Bellman equation essentially should be V star. So the time at k to n minus 1 will be time k to k plus 1 plus k plus 1 to n minus 1. Okay? So that's the Bellman equation. So now, because of the actuator saturation, for W you have that function, and then you have that, and then optimal control input is given by minus phi. That phi basically truncates the actuator output. Okay? So that's a function that truncates between minus something to plus something. You see that? And that's based on the actuator. Okay? So we don't have that phi before. This phi is now here, and then you have the optimal control input. So that phi was not there. This phi is coming from this phi, and that's basically for the actuator saturation, to accommodate the actuator saturation. Okay? So it's shown in this paper with non-quadratic cos functional 3, the control input 5, that's 5 here, is indeed an optimal control that minimizes the value function 4, which is given by that. Okay? So now we'll start looking at the quantizer, dynamic quantizer.
So remember the dynamic quantizer equation, UQK is QD, the mapping to Q of K. So that's in a dynamic quantizer, you basically taking a mu K here and mu K. Mu K is a zoom parameter. Remember the zoom parameter, we did that. And the purpose of the zoom parameter is what? What is the purpose of the zoom parameter? To bring that, to bring the values from outside the range to bring it inside the range. Don't forget that. Okay? So that's the zoom parameter there. So we have the zoom parameter, and there is an error, and that error is given by this term, is bounded, and the scaling pattern mu of k is defined as expected value of absolute value of uk over lambda. So lambda is between 0 and 1. So the signals to be quantized can be scaled back into the quantization range with a decaying rate of lambda k. So this is why you have these equations, 4.64, 4.65 and 4.66. So those three equations, what that does for the dynamic quantizer, they push the values outside the range into the inside the range, so there won't be any saturation. And the good thing with the dynamic quantizer is you need fewer bits. We saw that before, and as you increase the bits, the error goes to 0. Okay? So this is the dynamic quantizer equations. So now we are going to go into the controller. So here you see that we have the V hat, which is basically the critique, and we have the Bellman error. You can see the Bellman error equation. You also have the terminal constraint equation, and you have the total error En of k. Remember, the total error is the Bellman error plus the terminal constraint error. So we are using that to tune the weights of the critique network here. So this is the update law for the critique, which is given by equation 5. And this is the value function, right? And then here is the Bellman error. Now, since this is the output feedback, so this is the output feedback. Now look at that. The output feedback, essentially you are replacing the measured state with the estimated state. Don't forget that. Remember I showed you that, right? Because we don't have the measured state. Alright? But we use an observer. The observer design is from a few slides before I presented the observer design. And so the dynamic quantizer design is also there. This is the observer design. So only thing is I'm replacing the state with exact. Okay? So I'm computing the Bellman error. Bellman error uses the estimated state. And it also uses the extra term, which is non-quadratic functional, to accommodate the actuator saturation. Alright? So here is the terminal constraint error. And so the update law now uses the estimated state, the non-quadratic functional, and so this is the update law. Then you also do similarly, you also do the control input approximation. Control input error, U1 hat minus U2 hat. Now look at that. It uses the exact, which is the observer state. Okay? And then you are also updating the action network, which uses the input error or the, remember EUK here. So you're using everything observer state, also the input error. Input error also uses the observer state. And it also quadratic, non-quadratic, the phi. You see the phi there? The phi was not there before. The phi is coming here because of the actuator saturation, to accommodate the actuator. So it truncates the value of the command input that goes into the actuator. You see that? That phi. And you select that phi. So now you have two flowcharts. One flowchart is with the actuator saturation and input quantization. On the right hand side, there is no quantization. Okay, and there is no actuator saturation. But both uses the observer. Both use the observer and the identifier. So you see that first you initialize the observer states, the weights, you have the system dynamics, then you are using the quantization, in this case the dynamic quantizer. You have the update of the observer, then you update the identifier. Once you get the identifier, then you have the value function update, then you have the critique neural network. Okay? So you have the value function, the critique update, and then you have the control input. And action neural network update using this UU, and here is the Bellman error, terminal constraint error, here is the Bellman error update. And then you check the time. If the time is reached n, if time is not reached the final n, then k becomes k plus 1. Here k equal to k plus 1. And then you go back. Okay, so you see that there is an input quantizer here. You also can use a state quantizer. Okay? Here, there is no quantizer. So you basically observer, identifier, value function critique update, and control input. So basically there is no quantizer. So that's the difference between there is no without quantizer and with quantizer. Got it? So you show the mathematical results in these theorems. So let's take an example. So now we pick the same tooling robot. So the tooling robot that I defined here, we remember that tooling robot example. This is the tooling robot. Okay? So we are using the same tooling robot example. Alright. So now what I'm doing is I'm also looking at the actuator saturation. So I'm defining this value here. Okay? And the bounds on the saturation bounds are phi. Bounds is 1.5. So I chose the magnitude of that saturation. You can pick that based on the actuator. Alright? So sampling interval is equal to 5 milliseconds. Alpha 1 is 0.7, beta 1 is 0.01. The critique learning rate is 0.1. The actor learning rate is 0.03. The lambda value for the dynamic quantizer decay rate is 0.9. The Q weighting matrix is 0.1 identity. The R weighting matrix is 0.005. The terminal constraint value psi is equal to 3. Remember, we have to choose the observer A matrix, which is 0.9. You see that 0.9 is within inside the loop, inside the unit disk. So therefore, the eigenvalues are 0.9 is stable. Discrete standard. You understand that, right? So the observer gain now L equal to is selected like this, so that A minus LC, the eigenvalues are on within the unit disk. Any questions here, guys? Any questions there? Yeah.
While we choose the observer gain, we will follow the simple pole placement.
Yeah, pole placement A minus. A minus LC. You know C, we know A minus LC should be within the unit disk. Yeah, what is your question?
Sir, in the Bellman error which we defined, so there like we have the non-quadratic function forms.
Right. So here is quadratic, just to show you, this is not quadratic, here is not quadratic.
Right, so that's just the computation part, but the actual application of that phi function is in the
Control input. Actually, there is a derivation, and that's what the paper I cited. He showed that in the derivation, it only shows up in the optimal control input. So it basically scales the optimal control input. And the purpose of the scaling is so that it will be within that actuator limits. You see what I'm saying? The very similar idea we are using in the dynamic quantizer. by using the mu.
And also, like, do we take some specific set of inverse functions?
That is right. You have to pick based on the how you want it. So one example is the tangent hyperbolic. So you can pick a tangent hyperbolic. The good thing with that is it's very smooth and continuous. And or sigmoid like used in neural networks, you know. So you can pick any of those functions. Basically, it has a negative and positive side, and in between that is nice smooth function. You do want to pick a smooth function because it has to be Lipschitz, and it should be a one-to-one. So if you take the inverse, inverse should exist. So we call that term a smooth function whose inverse exists. What is the type of? There's a word that's being used in nonlinear control. How many of you took the nonlinear control class? And nobody is now raising. I see some people nodding. So you took nonlinear control? Did you take it here? Okay. So how about you? But did you take a course? The nonlinear control. So how many other than her? She's bored at least. She's honest. How many of you have taken nonlinear control? All of you have taken. So what is that name? They use a name. So the function is one-to-one mapping, and then when you go back also it has to be one-to-one. Yeah, I know. Yeah, what is that called? Nonlinear control. We use that. That's very important. Because when we do the transformation, then we go backwards. So it has to be continuous, both sides, and it should be one-to-one mapping. So what is that called? Now imagine, I'm even older than you guys, right? I remember. That's the learning part. You should be remembering that. See, in an interview, what do? If somebody asks you this question, let's say in a job interview, yeah. So what is that called? Have you heard of diffeomorphism? Doesn't ring a bell. Go back and check it. It's called diffeomorphism. Diffeomorphism. Check that. Okay? So what it means is the function is smooth, so you can map it from one set to the other, and the function has to be. And where does it come? In feedback linearization. Do you guys study feedback linearization? Is that ring a bell? No? Okay, what did you guys study in the nonlinear control then?
Neither. They are knowing, but this time they are not able to reconnect. Because
So I'm positive, guy, right? We teach feedback linearization.
yes, that is there.
Yeah. So in feedback linearization, we map from one coordinates to the other. So that mapping has to be continuous, one-to-one. And then after you get the results in the other set of variables, you map it backwards. And unless it's a diffeomorphism, you really can't do a one-to-one mapping. So I want you to go back to your nonlinear control notes or whatever, check it. And I'm going to ask that question tomorrow, right? Check it. I think it's important. These are all so all these concepts are also there. I don't teach them here, but those are needed. We normally don't deal with them, Okay, so any other questions? Okay, about the Kalman error? Any other questions there? Is that clear? Yeah. So remember, the Bellman error uses that actuator saturation stuff as well as the quantized state. Remember that, right? Because there's no normal state. So everything is a quantized state. So you have to use that in the Bellman equation, okay? And then if you don't have the quantizer, then you don't have to. In this case, there is a quantizer, okay? All right. So, but it also uses output feedback. That's why you have those hats coming in. You see there's a hat there, there's a hat there. Okay? So that's the observer state. So we do that. And in the update class, you have the critique update, which is very similar form, but you have the Bellman error with the quantized state, and then you also have the action error, But you see that you're right. There is the phi there. That phi comes in because of this term phi is because of the actuator saturation. Okay? And then you have that, alright? So let's go back to the example here. So we are using a tangent hyperbolic function here. You see that? The tangent hyperbolic is what normally we use. So there is a tangent hyperbolic. U is the limit, and this is the actual value. This is the bar, U. Okay? So now we have all these values. So now you can plot, you run the simulation, you can plot the error history, and you can see they nicely converge. So there are 4 states, converges. The quantization error also converges to 0. So now this is with our quantizer called dynamic quantizer. But if you use a uniform quantizer or static quantizer, there will be error. This is what we are trying to show. There is error here. See that? This is, I think, 4 bits or something. And you can see the Bellman error converges, the tenor constraint error converges, the critique weights converge, the actor weights converge. So this is with the output feedback and the system dynamics unknown. Okay? I think that's all I have here. Any questions? I think the only thing I didn't plot here is the observer errors. So maybe it's there, but I didn't plot and copy that plot here. So that I did the plot of the observer errors. But you know, in the other case, I have all got in the other examples that I showed you. They have the observer errors, right? Yeah, I see. There's an observer error here which goes to 0. And also in the other example, there is also the out. I think in the other example, I also plotted an observer error. So here I didn't plot it. Okay? Okay, any questions, guys? That's the quantization part. Any questions?
Sorry, this is in slide number 50. We have taken 3 neural networks only.
We use neural network. That is true.
3
Yeah.
Replicating and directing.
Yeah. And the actuator is all of the neural network and guide, and the phi is the tangent hyperbolic. So it uses same neural network. That's why I presented without quantization before, and then I added the quantization. That is correct. Uses the neural network. Okay, any other questions, guys? Any other questions? Alright,
Sir, here you have considered the actual saturation.
that is true.
The saturation means you are taking it out of the saturation by that dynamic tuning factor.
No. There are 2 kind of scaling factors. One is the actuator saturation. We use the non-quadratic function. See this in here, we are using that, this is a non-quadratic cross function. So this non-quadratic essentially, which is taken out from this paper, Levitsky. So this paper essentially you can select, right? Normally we select a quadratic function. This is what normally we select. Unconstrained. So with the constraint on the actuator, you basically change that this W function. The function becomes non-quadratic.
What is the nature of this phi function?
It's a diffeomorphism. It's basically a diffuse. Tangent hyperbolic is what I think. That's what I was saying. You see that it is a diffeomorphism because phi inverse should be bounded 1-to-1 and phi has to be bounded 1-to-1, you know. So it has to go back and forth, yeah.
Tangent bounded.
Yeah, tangent hyperbolic, yeah. So that's what I did here. If you look at the example, so you see that tangent hyperbolic? U is the limit.
So this will help not to cross the
That is correct.
saturation limit.
Saturation limit, that is correct. So here we are doing two things. One is we incorporated that stuff to accommodate the saturation issue. In addition, we also dealt with the dynamic quantizer for the control input. You see?
ADC part you are doing by zooming factor.
That is correct. That's right. So when I was covering this optimal control earlier, I said you could have some constraints. And one of the constraints could be on the control input. Because sometimes you still can produce a control input outside that range of the actuator. So the goal was, how do we bring it within the, just like the quantizer. Any other questions? Any other questions? So we also added the observer part. You see that? So we had some on state feedback. I'm also showed you some on output feedback. You see that? Because output feedback is very common in practice. We won't have sensors for every state, right? So this is the reason why I said that I was covering both state as well as the output feedback. And there is MATLAB code. You can play with it. Okay, any other questions?
Sir, I have some implementation regarding the question. So
Okay.
basically, in aerospace control system, for actual saturation, we mostly use NDI controllers or EDA controllers.
What controllers?
Or non-linear dynamic inversion.
Okay, yeah, inversion. But you know, inversion controllers have some issues.
Yes.
Yeah.
So if we are implementing that and we are implementing this dual control system, so if I am comparing whether, because I have never used this, but I have used non-linear dynamic inversion.
Right.
So which will the give optimal performance and prevent
Okay, I would not use inversion. I know in aerospace that's very common. And you know, inversion is always a problem, right? Remember, many reasons. One is, if the inversion is not exactly, then you don't get an identity.
Yes.
Usually the idea was, you have the nonlinearity and you are trying to invert that. And so that phi inverse phi is identity, right? That's basically the idea, and becomes linear. But there are, I know in aerospace I've seen that, but there are issues. Suppose there is some perturbation, then these two exactly doesn't match, you know? So that's the problem but even what I presented here was the actuator saturation still holds good. You can still do that, even with that type of setup, the inversion-based controllers.
But still, inversion-based controller, derivative.
I would not suggest, I would not recommend, because there are problems with inversion. Because what if the dynamics have some singularities? Right? Yeah. I know that in aerospace they limit, there's a guy, I forgot his name, he was in Georgia Tech, he does quite a bit on inversion-based controllers. And I had a lot of discussions with him, like he was doing helicopter control, and he was using inversion-based. There is a problem. If there's a little deviation, then, if they don't match, you get an extra term in there, because of it doesn't perfectly match. But here we don't have the problem. Because here the only idea of the inversion is mainly what you're doing is you want to make sure that you're pushing the actuator controller output values within that limit. You're not inverting it. You see? That's the difference, yeah.
So what is this? I don't know both.
Dynamic inversion. It's called dynamic inversion. So what they do in aerospace, like you have a nonlinear system, let's say some F function. They design a F inverse. Okay. So when you look from the input to the output,
Our problem is that F is a vector.
yeah,
So what is the meaning of that inversion?
you do that.
Each component will take the inverse.
Yeah, you take that.
Component
Yeah. And it will become identity. That's the main idea behind it. Yeah. It's the same. Yeah, they use it very well in the aerospace field. It's a problem. I never use it. The control guys in AA never use that. Only in aerospace you see a lot of people using it. Kalis, his name is Kalis. He's a well-known guy in aerospace. CALISE. He uses inversion. And very common in aerospace. So they put that in front of that system so that the overall becomes identity. Yeah. And naturally it will be always something's changing, and it is and people, they have analyzed it. It's been an old technique. But I don't like that, because if there is a singularity problem, you're stuck and it causes problems. Yeah. So like we do feedback organization, right? They don't do that. They put the inversion on it. So it's called dynamic inversion. Kalis, if you look at that, dynamic inversion. You look at any papers by Kalis, Anthony Kalis, CALISE. But a lot of people, Bernstein, there's a guy by name Bernstein. He's out in he writes tons and tons of papers. That guy is in Michigan. Yeah, he's an aerospace guy. He also, and I can't understand any of his papers, but a lot of math. But he uses dynamic inversion. Yeah, Bernstein.
He used to write how to do research.
Is that right? Oh, is that right? No, but that's okay. I don't mind that.
No, the control system magazine.
Okay, yeah, he is. No, he's a good guy. He actually, but he puts a lot of math and very little practical value there. So, yeah, but all these guys publish in SAT.
Yes.
He works with another guy in Georgia Tech. Not I also know him, but he is a good guy, but we have a lot of discussions on this. Because are you engineer or are you mathematician? Anyway, but yeah. Any other questions, guys? Any other questions? We are a little early now. 10 minutes.
Ask whatever is coming in your mind. You can ask. That is the best opportunity.
Yeah. After next Thursday, you won't see me.
Whatever, it may be a silly question. What is the problem? Ask something.
After that, virtual, nothing real. I don't know whether I'll come back here. Yeah, so. Any questions? I think maybe they should spend some time in running the. Yeah. So you probably would provide the code today, right? And the slides maybe. Slides they have.
Slides already.
There you already shared with them. So
This slide is already. No, this one not. 5 and 6. Last slide 5 and 6 I have.
yeah. So the slides and the code, I think you guys will then play. And remember, I told you in the afternoon. So maybe we should discuss a little bit. One is I want you to spend some time running the code. Try to finish catch up. If you only have the example 1, I would rather have you do 2 things, right, in all these cases. One is without the actual NCS part, and the second was with NCS. And we did that for linear. Then we went into nonlinear and we did the same thing, right? Remember, we had the without NCS, with NCS. So I would rather encourage you to spend more time and read the slides so that you know where are, right? Tomorrow we have another tutorial. And again, I also want you to study the Lyapunov stability. Some parts I skipped because that was not applied to NCS. So I encourage you to study those also, so that you can see the difference between how it's getting into the actual expected value or into the stochastic domain. So remember, we said asymptotically stable in the mean square. So you need to know a little bit, and look at the book. You guys have the PDF. Look at the book about why is it called mean square. Because in the proofs, you get the norm and then you have a square on it. So I encourage you to go through all that stuff. Okay? So this will give you some background, and so try to finish at least the MATLAB part of it. So how many, you asked them 2 problems, right? Inverted pendulum and the batch reactor.
But the other problems are also included there.
Yeah, okay.
If they want to try, they can try.
Yeah, they can try, yeah. It's very easy because you're just changing the system dynamics. Maybe you have to change the dimension of the vector. Yeah, okay? But it's all linear and positive, right? One non-linear is there,
Yeah.
but you haven't shared the code of the non-linear. Is there?
I've shared.
Oh, you did?
Problem 3 is that.
Oh, okay, okay. I see. I didn't see that. That's why I was asking. Okay, so you have enough to do as part of it, and try to do that. That's the best way. You learn and you come back with questions. Remember? So tomorrow we have 2 classes. In the morning, 1 lecture, and we are slightly ahead, just 1 lecture ahead, you know. And then we have the afternoon, which is tutorial. Okay? All right. So we take a break.
Yeah.
All right. If you guys don't have any, yeah. Can you raise your voice because then others can hear you? Right. Ah. Oh yeah. Sure. And the same thing like we discussed, even if it's tracking, the only thing is you have to have the system control. Okay, that's number 1. The other difference is you have to construct another augmented system. I mentioned this to you. If you are using neural network. Because remember I mentioned if you are using neural network, the trajectory which is in a tracking problem is a function of time. Right? It's an explicit function of time. In a regulation, all this stuff we are doing is a regulation. In a regulation, the trajectory is a constant, either 0 to something or something to 0, right? So it's always a constant, right? So since neural network doesn't approximate over the compact set I mentioned there, right? So you define a trajectory generator. Basically what you're doing is you're constructing the trajectory by like another state equation. Then you construct the augmented system with that trajectory generated state and the system state. That's it. And as long as it's controllable, you can do the same design. So you use the error now. Error is basically the desired state minus the trajectory. And there are papers available. You can look at it. Yeah. Okay? So it's no different. So her question was important. I was expecting that somebody asked you. So there are 2 basic control problems. One is called regulation. Other is tracking. If you do tracking, the same controller would work for regulation. But if you only do controller for regulation, it doesn't work for tracking. Why? You know that? You guys might have done that because you have taken the nonlinear control, you have taken some courses. So why is that? If you design a controller for regulation, it doesn't work for tracking. But if you do a controller for tracking, you can use it for regulation. No, even for regulation you can, I just said. Okay. Put it as a question. Why a controller for tracking would work for regulation, but not vice versa? Okay, can you check and come back? So you could do that. You could do the same thing, but this question is if you do it for tracking, tracking is much more powerful because tracking you have the time. You have the time. So it's a lot more difficult problem than a regulation problem. Okay? Any other questions? But you can. The controllability has nothing to do with the tracking or regulation. It's basically with the system property.
So even for the, you're talking about the nonlinear, but even for the simple state feedback controller,
Yeah.
when you are doing the regulation,
Yeah.
the same control will not work for the tracking
Right.
because there will be a steady state error. You have to modify
That's right.
u equal to minus k
Right.
something.
Right. Right. I think that's what I want them to tell me why it doesn't work. It doesn't matter whether linear or non-linear. You're right. You're right. Because she was asking this question for tracking, why does it work, and the controllability side, it does no matter, but not in the design. Yeah. And that's why I want that to come back. What is that extra term? All right, any other questions, guys? Any other questions? And he already has the answer, he already told, but I just want to see from you guys, what exactly is that? Okay? Any other questions? All right, no other questions, I think you'll have break for lunch.
So please go through the MATLAB programming. Okay. Once again, go with RL as well as yesterday, yesterday what I will share. Today also we will share the next assignment as well as related code. But I saw that it is exactly similar. If you have understood the first one, then consecutively others also. Only the modification you will see, that what modification in quantization and adding the neural network, okay, all these issues are there. Otherwise, it is like perfectly same. Because we are dealing in the same system.